Okay, let's talk about something that feels like straight up magic. How does an AI like ChatGPT actually understand language? I mean, really get it? Well, it turns out it's not magic at all. It's geometry. Yeah, you heard that right. Let's dive in. So here's the big question, right? How does a machine, a thing that fundamentally only understands numbers, how does it understand something as human as poetry? It can write code, it can explain quantum physics, but deep down it's just a calculator crunching ones and zeros. So how on earth does it get from a bunch of numbers to grasping the meaning of a poem? That's the puzzle we're going to solve today.
All right, so the first step in this whole process is turning a language into something a computer can actually work with. And that means one thing: numbers.
Yeah, this is like rule number one of all AI. Everything, and I mean everything, whether it's text, sound, a picture of your cat, it all has to get turned into numbers first. It's the only language the machine speaks. All that rich, messy human stuff has to be translated into a clean, ordered list of numbers. If you don't do that, nothing else can happen. It's the starting line.
So, what do these numbers look like? Well, they come in two main flavors: vectors and matrices. And the best way to think about this is with a metaphor. Let's imagine a giant, sprawling map of meaning. A vector, that's just a set of coordinates. It's a single point on the map that represents, say, a word or an idea. But a matrix is more like a set of directions. It's the thing that tells you how to get from one point on the map to another. It's the GPS for our map of meaning.
And believe it or not, the core thought process of an AI boils down to some pretty simple math. You take an idea, that's our starting vector, X, you apply the AI's knowledge to it, that's our big matrix, W, and what you get out is a new transformed idea, our output vector, Y. That's it. You start somewhere, apply a transformation, and you end up somewhere new. And this simple little operation, when you do it millions and billions of times, well, that's the engine that drives this whole thing.
Okay, so we have this idea of a map of meaning. But how do we actually create it? How do we make sure that the coordinates for a cat are super close to the coordinates for a kitten, but really, really far away from the coordinates for, like, car? That's the real trick, isn't it?
Well, the old way of doing this was with something called sparse vectors. And honestly, they were pretty clumsy. Imagine you have a dictionary of, say, 50,000 words. The vector for cat would just be a list of 49,999 zeros and one single one in the spot for cat. Super simple, but crazy inefficient, and it tells you nothing about what cat actually means. Today, we use dense vectors, or what we call embeddings. These are much shorter, packed with complex numbers, and they're specifically designed to capture the semantic meaning of a word. It's a huge upgrade.
But here's the crucial trade-off. With these dense vectors, the meaning gets a bit fuzzy, for us humans anyway. You can't just point to one number in the vector and say, that's the furry dimension. The meaning of cat is smeared across all the numbers. So we sacrifice that easy human readability, but what we get in return is enormous. We get incredible efficiency, and more importantly, we force the model to learn the relationships between words, not just what they are.
Okay, now we get to the really wild part. Because once you've built this map of meaning, you can do something that sounds impossible. You can do math with words.
So how do you measure if two words are close on this map? You might think you just measure the distance, but in these crazy multidimensional spaces, that doesn't really work. Instead, we use something called cosine similarity. And the idea is brilliant. Forget distance. Let's look at direction. Are the vectors for cat and kitten pointing in roughly the same direction? If so, they're similar. Are they pointing in totally different directions, like cat and car? Then they're not. It's all about the angle between them.
And this idea, this focus on direction, is what lets us do that word arithmetic I was talking about. It's amazing. It means abstract concepts, things like gender or royalty, they literally become directions you can travel in on this map. Let me show you the classic example that proves it. All right, first step, we find the vector for the word king. Just picture its location on our giant map. Now for the math, we're going to subtract the vector for man from it, so king minus man. What does that leave us with? Well, in this geometric space, it leaves us with a new vector that represents the concept of royalty stripped of its maleness. It's the pure essence of monarchy.
And then, for the final step, we take that royalty vector we just made and we add the vector for woman to it. So we have king minus man plus woman. And what point on the map do we land closest to? You guessed it, queen. I mean, how cool is that? It proves the model didn't just memorize definitions. It figured out the underlying relationships between concepts, all on its own. It's all just geometry.
But that's all about what words mean in a vacuum, right? The real magic of modern AI, like ChatGPT, is how it understands that the word bank means something totally different in riverbank versus money bank. It understands context. And for that, we need to talk about the transformer and its secret weapon, the attention mechanism.
So for every single word, the model creates 3 new vectors called the query, key, and value. You can think of it like this. The query is the word shouting, "Hey, I'm trying to figure myself out. What other words here are important for me?" Each key on every other word is like a little name tag that says, "This is what I'm about." And the value is the actual juicy information that word has to offer. So the query looks at all the keys to see who's relevant, and then grabs the values from the most important ones.
It all happens in this lightning-fast 4-step process. First, every word's query checks out every other word's key to get a relevant score. Second, it does a quick bit of math to scale those scores down. We'll get back to why in a second. Third, it turns those scores into nice, clean probabilities. And finally, it creates a brand new vector for itself that's a mix of its own information plus a little bit from all the other words based on how relevant they were. The result? A word that now understands its place in the sentence.
Okay, remember that second step, the scaling? I want to zoom in on that because it all comes down to this one little bit of math.
You're looking at what might be one of the most important little tricks in all of AI. Seriously, without this scaling factor, the math inside the model would just explode. The scores would get too big, the model would become way too certain about its decisions, and the whole learning process would grind to a halt. This tiny number is the unsung hero that keeps everything stable and makes it possible for these giant models to actually learn anything useful.
Okay, so we've got the map, and we've got the context engine. But that leaves one last question. How does the AI build that map and refine it? How does it learn?
It's basically a giant feedback loop. First, the model makes a guess, like trying to predict the next word in a sentence. Then it looks at the right answer and measures how wrong it was. That's the error. Next, using a whole lot of calculus, it figures out exactly how to adjust its internal wiring to make a slightly better guess next time. And finally, it makes billions of teeny-tiny adjustments to its parameters, ever so slightly nudging that whole map of meaning into a more accurate shape.
And that's really the whole secret. You just repeat that simple loop, predict, measure, adjust, not once, not a million times, but trillions of times. And over those trillions of repetitions on nearly the entire internet's worth of text, that simple process slowly carves and refines this incredible, high-dimensional, geometric space. That's how an AI that's smart.
So, that leaves us with one last kind of profound thought to chew on. We've just walked through how AI intelligence, this thing that can write poetry, is really just navigating a complex geometric space. Words are locations, ideas are directions, and thinking is just a journey across the map. So if that's what machine intelligence is, what does that say about our own? Is our consciousness just a different kind of geometry? I'll leave you with that one.